All right. Hey, everyone. So welcome to another episode of me working on my Vectrex emulator. So last time I was working on this, I was pretty tired and got to a point where I had to implement the add operation and wasn't quite doing it right, so I decided to wait until the next time. Since then, I've taken a look a little bit at this code and started refactoring it a little bit. And I would like to continue actually where I left off just a couple nights ago when I was working on this. So basically, I'm in the process of implementing the add, subtract, and I want to also do add with carry and subtract with carry. So the four basic arithmetic operations. These are surprisingly tricky to get right. There's the complication comes with the fact that you can't just write subtraction or addition as you would normally in C++, because you have to take care of doing the 2's complement of the values yourself. For subtraction, you need to also track the carry bit to make sure you update the flags correctly. So every time I work on this, like the first time I work on this on the NES emulator, it didn't quite work right, and then it took me a little while to get it right, and looks like I'm going through the same thing here. Actually, I'll be right back. Just give me a second. All right, sorry about that. Stop the music. Okay. So yeah. So what I was saying was that it's always a bit tricky to get this right, and I was looking it up because I was like, am I the only one who has trouble with this? And I was looking this up. Somebody actually asked on Stack Overflow, like, proper way to implement ADC and SBC. And I thought that was funny because the answer here is like kind of funny. Welcome, brave adventurer, to the arcane halls of the 6502 add and subtract commands. Many have walked these steps ahead of you, though a few have completed the gamut of trials that await you. Stout heart. So, yeah, I'm not the only one who finds it a pain in the ass to implement. Anyway, so I'm going to keep working on this today. So what I was doing last time is, the way I'm trying to do this actually is to write subtract in terms of add, because like as is explained in the one of the answers here, and it's correct, is what you want to do is you want to do the ones complement of when you want to do subtraction with a carry. What you take is you take the value you want to add to your register, in this case it's arg, you flip the bits, so that's getting the ones complement, which is basically the same as minus arg minus 1, and then inside the function you want to add the carry. So when I was working this on last time, I turned it into a 2's complement value with by doing the complement of b plus 1, but I think that this is not giving me the right value for my flags. So what I was thinking last time is what I need to do is I need to pass in the kind of like the carry value that I want to add, which in this case would be a 1, but I believe might be plus 2 for carry if there's a carry set. So I'm not sure yet. I'm gonna try something. It's because to test this, to test my code, what I've done is I found online this Frank's cross assemblers here. He has a bunch of assemblers for Windows, and the one that I need for my CPU, the one that's in the Vectrex, is this AS09. This assembler for the CPU that is the Motorola 68A09. So there's that 09 in there. So this assembler actually assembles into the right format for this CPU. So I downloaded it. I have here, so this is where the assembler is, AS09, and I wrote a little test file, test.as9, which is over here. So this is like a test ROM for the Vectrex emulator. There's some ROM header and stuff, but really what matters is here is I have this like section of code for test add and a section of code for test subtract, and all I'm doing is I perform these operations, and then I run this in my emulator, and I look at what the flags look like, what the register values look like, and to compare it, I also found online, so actually I think I may have shown this in another stream, here, just move this here, okay. So I found online, this is kind of cool, it's somebody wrote I think it's in JavaScript or something, but it's basically a compiler, an assembler and debugger with an emulator and everything for different CPUs. So you can see up here ZX Spectrum, there's a 6809, which is what I'm using. It also supports 6502, which is the same as the NES and Apple II. And a few different other chips here, the Z80. So what I do is I write my code and then I copy, actually I don't copy all of it because it doesn't like this part here, but I just copy like from here downwards like this, and I go, sorry, I have to get out of the emulator. So this is where you enter code. So I just put it in here, compile it, it compiles fine, and then I can run this emulator where I can step. So here I was in the process of testing subtract. So I'll execute 3 instructions here. So load load into register A the value 0, then store at RAM start the value that's in A, and then what I do is I say subtract. Actually, I don't even know why I bother storing it. Why did I do that again? I don't know. Anyways, I guess that's completely useless. I kind of just copied this pattern I was using earlier. I guess I wanted to see the values in RAM, but yeah, this is kind of useless now that I look at it. But anyway, the point is that the important part is I subtract from A the value 1. So this is basically doing 0 minus 1. So when I do that, so actually I'll reset here. Reset. Okay, so like load A, subtract. So that should give me a value of minus 1 in A, which it does, which is FF. And more importantly, what I'm concerned about is not just the result, but the way the flags are supposed to be updated. So I was working on this a couple days ago, so I'm not even sure if what I wrote here is correct, but yes, it is. So here we can see what the flags are set to in this emulator. The important parts are the last 4 bits. That shows us whether the negative flag is set, which it is in this case, which makes sense since it's minus 1. 0 flag is not set because the value is not 0. So those are like 2 easy ones. The ones that are more complex to get right are overflow and carry. So here overflow is not set. And overflow is basically the bit that gets set when you treat your values as signed values and when the operation that you perform ends up changing the sign incorrectly. So like if I say add 2 positive values and it produces a negative value, then overflow will be set. Or if I add 2 negative values and get a positive value, then that's also incorrect. So again, overflow would be set for that. And carry, well, carry is basically for unsigned values. And the carry bit, the carry flag here gets set for addition when you add 2 values and it causes the last bit to overflow. So like the most significant bit, when you add the 2 for, let's say, the 2 values, if they're both 1, that will cause an overflow. So like 1 bit will be carried out. So that's when the carry will get set. For subtraction, from what I've read on this CPU, the carry acts in the opposite manner. If no borrow occurs, the carry gets set. But if a borrow occurs, it's unset. So in this case, when we do 0 minus 1, it's saying that no borrow occurred, right? If carry is high, it means no borrow occurred. So this is what I need to get right on my side, and I'm not getting it right yet. So I just wanted to work on that today. Hey, peas and rice. You say that carry logic is nice and backwards. Yeah, it totally is. Yeah, it totally is backwards. And I mean, I guess it makes sense. Okay, so welcome to the stream, Andy. Thanks for joining. Okay, so let me show you what this looks like when I run it in my emulator, just to kind of compare the two. So here I'm just going to run my assembler here on my test file, and then I launch my emulator, which goes into my debugger. So I step, and basically I'm in the part of the code. So this is branch at 2b. So this should be the test subtract. So right now we're doing load 0. Then we're going to be doing a store at this address here, which corresponds to RAM start, which was set up here to C880. So that's correct. And then we should get a subtract A1 here. And now at this point, I look at my registers. So we can see that A indeed gets FF, which is -1. So, and we can see here already this is not right. In my flags register here, I have capital N for negative here, which is right, small z 0, no overflow, but I have no carry bit set. So I think I know why, and I just want to see if I can fix it. I'm not 100% sure, but I'm going to try something. So here, what I wanted to try to do was I have A, B, and I'm going to call it carry, and I'm just going to add it here like that. Like that, same thing here. Now, I wanted to do that because I wanted to see if the result of this, when I calculate carry, I want to calculate it as a result of whether or not it overflowed at this point in time. That's it. Like if the carry bit came out here. So here I'm adding 8-bit values, but I use a 16-bit result so that I can check if the, for example, for the carry here, I'm going to check if like the bit overflowed into the high 8 bits out of the low 8 bits. So I'm just really checking to see if the bit was set at position 8, at bit 8. So let's see if I do this, and instead of adding 1 here, I just pass 1 here. I have no idea if this is going to work. It also means I need to pass in 0 in all the cases where I don't care. So for adding, like that. Okay, so let's just see how this looks. And I might need this code I commented out. Because I think what happens is if it carries out, so the way it's working was when I subtracting is like the same thing as adding the negative value, right? So that's what we're doing. We're taking the 2's complement to turn it into an addition. Now if it carries out, we need to, that's like, I think that is the same as a borrow, in which case we want C to be 0. So I need to invert the value of carry in the case of subtract. So I think that's what we're going to see here, that it's not quite right just yet. No. Okay, so let's say we do that, and we put this back here. So we invert the value of the carry in the case of subtract. So obviously that's going to give us the right answer for this first test case, which is like the simple test case. Or not. Oh no, sorry. I'm missing one subtract there. Okay, there we go. So this looks right. Now, the next cases are the ones where I had a little bit more trouble. So I want to see. So the next case is 1 minus 0. So in 1 minus 0, it should be like this. Non-negative, non-zero, no overflow, and no carry. So let's see if that's right. Yeah, so that was the 1 minus 0. NZVC, that looks good. So now we do 1 minus 1, which should give us 0 and A, which it did. And we get N capital Z, small v, small c. So yeah, here in my comment I don't have it right, but that's what I should get in my emulator. So let's see if that's the case. Yes. Okay, that's good. So yeah, okay, and then the next case that I had, okay, where am I? Oh, that's it. Those were the 3 cases I had so far for negative. Okay, so that's a good sign. Let me just fix this comment here. This would be lowercase c. Reset. Yeah, and this one as well. Yeah, it's super confusing. When I wrote these test cases, I thought the carry would be set if it had to do a borrow. And then I read, it was in this doc that I have here for subtract, and it said, the C flag represents a borrow and is set inverse to the resulting binary carry. And then it says for carry, set if the operation on the MS byte did not cause a carry from bit 7 in the ALU. So that kind of corresponds. So if there was no carry that occurred in the ALU, when adding the 2's complement, then you know, if it did not cause a carry, then this is actually set. Super confusing. But anyway. And the other part of the fix is this passing of 1 inside, because what was happening is I was adding it before, but because this input value is itself, like in the case of an 8-bit add was passing in an 8-bit value, then that +1 would overflow in 8 bits on, you know, on our CPU, like on my Intel CPU. It would overflow the value and then pass in an overflowed value. So I wasn't getting the carry bit overflowing where I need to know about it. So that's why I'm going to pass it in instead. I think this is right. We'll see. Okay, so I just need to double check. I want to double check that my adds still work. So I'm going to just change this code to jump to the test add instead. Compile that. Put this in here. Okay, so let's do test add. Oops. All right. And compare some values. It's kind of hard to compare on one screen, but we'll do our best here. Let's go like maybe like this. All right. So all lowercase, and that is not, okay, I haven't run it yet, so here we go. So just Z is set, that's correct. All right, step, 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 info reg, and step, step, step. All values are low, all values are low, so that's good. For the next one, negative is set, and only negative is set. Okay, good. Again, only negative is set, which is not correct. Oh no, sorry, did I? Yeah, I did run it. Did I? Let me see where I am. B7F is the add A that I just did. Okay. Where did the current PC is 001E, so I'm here. Okay, let me just restart this because what I really wanted was this one here. 128 plus 127. Oh, it's because I missed a step here. There we go. 128 plus 128. Okay. Here we go. So N, then ZVC. Okay, that's good. Phew. Thought I broke that. You missed it? What did you miss? Oh, nice. Okay. All right. So next one will be 120 plus 10. So we can see here the value. It says 120 here. Again, I don't know why I'm storing it. And then I add 10. And then here, so negative and overflow. And yes, negative and overflow are set. So that's good. So the last one is minus 50 plus minus 50. And on our side here, so minus 50 is actually 206, which makes sense because it's 256. And then we add minus 50. In that case, negative and carry are set. And that's negative and carry. Okay, good. And then I think we fall into, it just continues into the testing of subtract, which we just tested. Yeah. Bob Ross meets Vectrex. Is that because of the colors? So colorful. Okay, this is pretty cool. So this is looking good. Trying to think if I, okay, so that's, so 0 minus 1, 1 minus 0, 1 minus 1. I'd like to now test a case where an overflow would occur when I subtract. So that means like if I take two positive numbers and subtract them, no, two negative, yeah, I guess two negative numbers, if I subtract them and it becomes positive, that would be an overflow. So let's try like, 120 minus 10. Sorry, minus 120 minus 10. So that, yeah, that should cause an overflow to occur. So yeah, I have no idea why I was bothering with all of these. I'm just going to remove them. I might need it later because there's some instructions where you specify an address and all that, but I don't need this for this. I could just use immediate values. So if we load into A minus 120 and then we subtract from A 10. Just that. So we go back to just testing the subtract. We compile this. Let's run our debugger. Oh, so I went a bit too far. Basically, it's instruction 29. So I can actually just say run until 29. Should that not cause an overflow? Let's see what our emulator here says. Yeah. So exactly, only overflow was set. For me, negative was set. That's super weird. You see here. So there's 88 in hex. And then we say subtract from A 10, which leaves me with 7E. Oh, I didn't actually, okay, yeah, this is something stupid in my debugger where when I say until 29, it runs, stops at 29, doesn't execute it, but prints it, which is super confusing because then when I step it, it prints it again. I really need to fix that. It should not print it. It should just stop there and do nothing. But yeah. Okay, so now, there we go. Okay, 7E is in A, and only overflow is set. Okay, that's good. All right, what's the next thing I want to test? So we've tested 0 minus 1 caused a borrow. And it caused it to be negative. This is positive. This is still positive, but 0. And this is ends up overflowing, so it ends up not being negative, not being 0, overflowing. And so if C is low, it means it borrowed, right? Yeah. Okay. And maybe a case of that doesn't overflow, that works correctly. So minus 50 minus 50, which should be negative. Non-zero should not have an overflow. And should not cause a borrow, so capital C. So we load A with minus 50, and then subtract from A minus 50. Compile, assemble this, and rerun my debugger on it. So that's the minus 10. So here's minus 50. Okay, minus 50. Not at all what I thought. Did I do this right? So minus 50 minus 50 should give 100. Let's see what the online emulator says. F10, no, F9, F10. C. One, two, three, four, five. 2, 3, 4, 5. And here, CE, yeah. Load ACE, subtract ACE. Which leaves A at 0. Oh, right. I meant minus negative. I'm such an idiot. Right? Wow, that's exactly what I'm... No, that's it. I meant like this. Not subtract minus 50, subtract 50. That would make more sense. Of course, it's going to be 0 if I add 50. Yes, Andy, you are 100% correct and saw that while I did not see it. So let's try that with a proper subtraction. Okay. That is, I think, carry not set, which is probably right because I keep getting it inverted in my brain. Yeah. So, I know I didn't actually do this yet. Let's put the, I guess this is just subtract 50 here. Assemble it. Okay. So that's good. That looks really good. So it's just negative that gets set. Okay. All right. I think I'm sufficiently happy with these tests. I think I've covered all the cases, right? VC, VC. Well, what I haven't covered is both overflow and the carry set, which I don't even know how to do. Yeah, not even sure. Okay. But, I mean, I'm satisfied. I think the code is good now. It makes sense. It's carry set if no borrow occurs. And the next thing I just wanted to double check was, because the compare instruction makes use of subtract, we discard the result, but we use it to update the flags. And I just wanted to double check on that, because it's kind of important. Andy says, very cool, awesome job so far. Thanks, Andy. Okay, so let me just double check on compare. I want to go look in the doc how it's defined. So compare memory from a register. So n is set if bit 7 of the result is set, which makes sense. Z is set if all bits are clear. Overflow is set if the operation caused an 8-bit 2's complement overflow. Yeah. And C is set if the subtraction did not cause a carry from bit 7 in the ALU. So it sounds exactly like subtract, which is why I wrote it in terms of subtract. Compares the contents of M memory from the contents of the specified register and sets appropriate condition codes. Neither M nor R is modified, which is true, yeah. And the C flag represents a borrow and is set inverse to resulting binary carry. So yeah, this really should work as one would expect. So if I wanted to test compare, in this case, that's it. I would need to write to memory. So that should be easy enough to test. Jump to test compare. So first, let's load 0 into A, and this time we will store it. Store it into RAM start. And then compare. Does it work again? I think it's like compare A. Yeah, I can do compare A with RAM start. Oh, yeah, and what do I want to compare? So this would be comparing 0 to 0. Because this is basically doing like the same thing as 0 minus 0, which I actually didn't test. I should do that actually. Which should do no negative, which should set 0, no overflow, and no carry, I think. Subtract from A, 0. So let's just go back to this part. It'll be the first of test subtract. Subtract 0. So yeah, my guess was right. Double check that this makes sense. And here. Yeah, okay. So we should get the same result when we try to do our compare. Right, so like that. And now we'll do basically a compare against 1. So basically 0 minus 1. So basically all these are the same cases that I have here. So we have 0 already at RAM start, but I'll just do it again. This time we load 0 into A, store it there. Now we load into A my 1. Yeah. So we want to compare. No, is that right? Now we want to write 1 into memory and then compare 0 to 1. And that's the same thing as doing, because it's register minus memory. Memory from a register. Register minus memory, yeah. Okay. Let's just see if this looks good so far. Compare A. So yeah, and just run this in the other emulator. So only 0 set, that makes sense. Now we load 1 into A and store it into C880. Load 0 into A and do a compare. In which case, negative is set and C is set. Oh, that's interesting. Overflow. Why would overflow be set? Okay, let me just go C880. There's 1, which is what we stored. And we loaded 0 into A, and we compared A against what's in RAM start. Should be 0 minus 1. Yeah, B1, C880. So the only difference is that for some reason I don't have overflow set. Which would make sense because it should behave the same as 0 minus 1, right? Let me see. Let me see what happens. I'll debug this specific case. Put a breakpoint in my compare. I think it's the 8-bit one. Here. So the register has 0, which makes sense. And we're going to do a subtract. We're going to read the value at this effective address, which should return a 1. Yeah, it returned 1. Now we come here. A is 0, B is 1. So we will step into add impl. A is 0, now B should be FE, which makes sense, plus carry of 1. So then R16 is 00FF. I don't understand why this would cause overflow. Where am I looking? Okay. So what I'm looking at here is what should be basically the same as doing 0 minus 1. So I load 1 into A, and I store it into RAM start. And RAM start points to, is basically just a name for this address, C880. So you can see there's the 1 that I stored. Then I load 0 into A, and then I say compare A against RAM start. So that's the same thing as saying A minus RAM start. And I just want to make sure that the flags are updated right. So I expect it to behave the same way in terms of setting flags as 0 minus 1, which we saw over here would set it like this, you know. Right? Just double check. I mean, it makes sense. I don't think there should be any overflow that occurs because 0 minus 1 is minus 1. So there's no like, you know, weirdness of I took a positive number minus a negative number and I got a negative number. So that's fine. There's nothing weird about that. Like, if I come here, let's make it go back to jump subtract here. Assemble. Yeah, see? I just subtracted 0 minus 1 and there's no overflow, right? And yet, when I come down here to what is equivalent, or at least should be equivalent, super weird. Okay, just a second. Just open this book and the PDF viewer in here is not as good. Can I duplicate? Yeah. Okay. Can I pull this out? Good. Sub. So like we can see that it's basically compare and subtract do the same thing. It's r minus m into temp. Because the idea is we don't care about the temp, but we just care about the flags and how those are updated. Okay, so Andy says line 386. Where am I looking left, right? Right? Am I right in saying carry shouldn't be set? I'm actually not looking at carry. In fact, my carry seems to be correct. I'm looking at the overflow. For some reason, they don't. Like I thought, you know, I'm just going to implement my compare in terms of subtract because that's exactly what it's doing, and it should be updating the flags in exactly the same way. Unless I can't trust this emulator, which would kind of suck. So Andy says there shouldn't be an overflow, right? No, there shouldn't. I mean, that's, you know, my code does not produce does not set the overflow flag, yet this emulator here does. Yeah, I know. Me too. Like, yeah, it's like reloading all that stuff we learned in school about assembly and two's complement and how that works. 6 years for you? Yeah, it's a bit longer for me, but I did write that NES emulator like 2-3 years ago, so I did have to deal with some of this, but I actually forgot it all. And this is slightly more complicated than what I had to do for the NES CPU. I don't know, I was really trusting this emulator here to be correct, but you know, it's possible. Why would it set overflow? Why would it behave differently? Is there something I'm missing? So, okay, so you wrote here 0 plus 1, 1, 1, 1, 0. So basically 0 minus 1 is actually the same as 0 plus minus 1, right? Which is plus, and the complement of this would actually be, and actually would be, the 2's complement would be like this. But the fact is, it's with 0. So it's impossible for there to be, okay, no, sorry, it's impossible for there to be a carry. But even for overflow, right? Like, so yeah, this is FF, right? Like that's the result of 0 minus 1. For overflow, we're supposed to look here. And basically, if we have, this is positive and negative. So positive and negative, we don't care about the result. The only cases that we care about for overflow is if it's both positive, let's say 0, 0, and it produces a negative. That's wrong. Or if it's both negative, so 1, 1, and produces a 0. Otherwise, if it's 0, 1 or 1, 0 here, we don't care because we can't know. So it should not set overflow. So I'm inclined to believe that this is wrong, which is kind of scary. It makes me think I can't use this. I can't use this emulator to test my stuff, which sucks. So I might have to find another one. One thing I want to try is, what if, just for fun, if I load it into B and compare B, does it do exactly the same thing? And it's F8. Oh, sorry, test compare. So now B has 0, and then I compare it. Yeah, same result. Right? Actually, I need to reassemble what I've got here. Oh, I didn't actually change. It's like, where's my B? I didn't change it in my test. I just changed it in the emulator. So I put B down here. Load B with 0 and compare B to RAM start. Assemble that. Load B0, compare B. Yeah. Is everything 8-bit? So no. A and B are 8-bit registers. So this compare is a 8-bit compare. Then there are other registers. So D is actually a combination of A and B. So this is actually the value of A and this is the value of B. So a bit like EAX for the on Intel, how it's like AX and AL, right? So it's like basically you're just addressing the two registers as one. So that's a 16-bit register. And then you have X and Y, which are also 16-bit. They call them indexing registers, or index registers. U is a user, the user stack pointer. So again, a 16-bit. S is the system stack pointer. This is the direct page, I think, register, which is 8 bits. Then the program counter, which is the instruction pointer, and then the flags. So I could also, that's true. I haven't tested the 16-bit versions of adds and subtract. I should definitely test those. But for now, yeah, I don't know. I don't know what to make of this. I really don't think it's wrong based on what I've read and what I've implemented. Yeah, it makes sense. So Andy says, I'm wondering if there's a control bit or something weird going on. I don't know. All right, well, Andy, thanks for hanging out. And yeah, maybe next time you come on stream, I'll be a bit further along. But thanks. Take care, man. All right. So let's see. I could try 16-bit. It will be completed, I'm sure, says Andy. Yeah, I hope so. I'll try and compare with D just to see if it behaves the same way. reading line 100. Okay. So let me try and take this code and run it in this online emulator that I now have not much confidence in. Although it's probably okay and it's just me. Okay, so let's see here. So we load 1 into D, which puts 1 into B because that's the A and B are D. We store that at RAM start. So RAM start is C880. Just want to go see. Yeah, so that makes sense because now that we're storing a 16-bit value, it puts it in the low byte here. Then we load D with 0. So there we go, 0, 0 here. And we compare D against RAM start. So 0 against 1, so 0 minus 1. Aha! This time, no overflow. What? That's so weird. That makes no sense. $34. Single step. Why would this happen? Load 0 into B, compare B to RAM start, which is 0 minus 1. Don't get it. I wonder if there is another way I can test this. Another thing I wonder though is maybe overflow doesn't matter for compare instructions, because for compare we're supposed to use like greater than and all that, and those don't look at overflow. Even though it is going to be computed, maybe it's just not useful. Maybe I'm wrong. Okay. I'm going to assume what I have is fine. And I'm going to check this in. So let's commit what I've got. What did I do? Right, I had carry. Okay. All right, so this change is fix computation of carry flag for add and subtract. CPU instructions. I also want to commit this change that I made to the debugger, which is debugger invert display of CC flags to match order of bits. Bit 7 display first down to bit 0. Okay, and this I don't want to check in. So let's see. So now let's see, I think the next instruction I'm going to have to implement is add with carry. So let's just see how far we get in the debugger. I saved off here what I usually need to do when I start my debugger. So load symbols from this file, set the dude register to FF, and then off we go. Or not. All right. Yeah, I gotta not load my test ROM. So if we go back to main, let's not do this. So I'm going to continue running the BIOS. Last time I got pretty far and then I got stopped on an add instruction, and I implemented that now. So what we should see, I believe after the add there was an add with carry. So let's just see if that's what happens. I gotta fix this really slow printing. I now think I know what it is. I was thinking about it, and I'm pretty sure it's because I am flushing standard out after each print. Yeah, like, okay, so there's an endl here, but it's not the one. So like here, print op. The fact that I have this end line here, this flushes the output stream. So what I should probably do is take this off and just make sure to flush it whenever I need to break into the debugger. Like when I hit Control C. So when I'm about to take input. And then it should go faster. Actually, you know what? I'm gonna try it. Let's just start by, I replace this with a new line instead, which is not going to flush. And let's just see what happens there. Oh yeah. That looks faster. I mean, unless I'm, you know, maybe it's placebo effect or something. No, that's definitely faster. I don't know. No, that's slow. I don't know. Is there other ones? So that's when I break. Breakpoint, delete, print. So that's, yeah, I don't know. This seems, I guess this seems buffered. I'll have to do some tests. But for now, it's fine. Maybe I just need to increase the buffer size or something. I'm just paying attention to the addresses here. Just wondering if are we like in an infinite loop, or is this actually strange? It looks like we're stuck in some kind of infinite loop now. Okay, let me just break here. And let's see here, what's happening? Test, vex sound shadow, vex text width. So here we're loading the string pointer. So normally this means we're trying to print a string on screen. So at this address here, let me just make sure. It could just be that it's really taking a long time. This is such a slow... You know what I'm going to do? I'm going to turn off the trace for a second and see if, because with the trace off, it should go much faster. So we'll see how far we get. We'll see if we actually hit a unhandled instruction. Oh, right. I totally forgot. I do need to load my symbols and set that register this way. Okay, let's continue. Oh, here we go. Okay, so it was just taking a really long time. And there we go. We're at the unhandled op, add C, so add with carry the A register. So that'll be the next instruction that I need to implement. It's really a shame how slow it goes when I have the trace enabled, but it's all right. I'm also thinking that when I have an unhandled operation, it would be really nice, rather than have it fail like this, it would be cool if I could just break into the debugger, because then I could like see where I'm at and look at yeah, I'll make a note of that as well. So debugger catch exception from CPU for unhandled op and break into debugger. Okay. Okay, so the next instruction would be add with carry. ADC. Add with carry memory into register. So adds the contents of the carry flag and the memory byte into an 8-bit register. So I should be able to just implement this in terms of my add impl now that I have a carry parameter. Yeah, it should be as simple as that. So let's do that. So we'll go into the CPU and to the opcodes, split, ADC. So there's ADCA and ADCB. Is there a... Okay, so it's only for 8-bit. There's no like add with carry. Yeah, that makes sense actually. Okay. So let me get all of them. Copy. Add. Okay, so this is add, this is subtract. Okay, I'll stick add with carry right after. Like this. It'll be op ADC 0 and then break. I need to duplicate my instruction value here and grab these parameters here. Okay. Add CA and add CB like this. Okay, so I'm just going to copy this one here, because that's really what it is, and add with carry. Instead of passing C, we pass cc.carry. And we do update the half carry in the case of add with carry. So that should be it. Oh wait, I need to If I put a breakpoint, make sure. Oh, unmapped address. Okay, so that's new. So it wants to store a value at CFFF. Huh. Okay, I think I'm doing this wrong then. In my range here, what did I do? First and last. Well, that's it. Last is inclusive. Yes. So there may be a problem with, I think it's the first time we get an access to the last value in a range. So in my find device, this should have been less than or equal to the last address, because it is inclusive. Just let me make sure everything looks correct for that. Yes. Yeah, okay. So that was invalid. Let's see how far we get now. Okay, so now I'm a bit at a different place. I'm trying to increment an address 0xD800, which is unmapped. Does that make sense? No. Oh, it does mix. That's both via plus RAM selected. So this is supposed to be illegal, writing to D800. Okay, so now I'm kind of a bit blind because I don't have any trace output. So before I go further, let me just get this add with carry checked in. I also want to check in this fix here, commit the fix to the memory bus. So fix, what is it? Fix memory bus erroneous assert when accessing, sorry, fix memory bus not allowing access to the last address in range. Another thing I'm wondering is, it's possible that the main reason for the slowdown that we are seeing here is because of the colors. It's kind of been my fear that as cool as the colors are, it means that the console needs to keep switching state, so it's possible that that's causing it to go slowly. So what I would like to try here is, what if I output all this without that special coloring? what would that look like? Let me just try it. So it's this plus this plus this plus this, and finally that. Oh, no, that. And I can put the new line in here. Static, cool, with color. Okay, let's see if that's any faster. Oh wait, gotta turn on trace again. Yeah, I don't know if that's faster or slower. Probably just console buffering. Let me see. Windows, console, yeah. Printf or cout, set buffer size. Maybe it's time to move to printf. Because I'm not really making use of any of the features of cout. I am using cin.getLine though. Okay, so that here talks about performance for input buffering, but in my case it's more about output buffering. Once standard cin is constructed, standard cin.tie returns standard cout, and likewise. This means that any formatted input operation on standard cin forces a call to out flush. Okay. Sure. I mean, I'm not prompting the user, so it's fine. Cout, improve performance. Here we go. Let's see what Stack Overflow says about this. Printf could be much faster than cout, although printf parses the format string in runtime. Cout is always fast in printf by any means. Really? Yeah. Here is a hacks that should make C++ streams as fast as cprintf. Oh man. I mean, I tried this last time. I don't think it actually makes a huge difference or any difference. It's exactly the same. I really wonder, is there not a way to set the buffer size for output? No. So if the buffer is a null pointer, resizes the internal buffer to size. I think I read this one already. Right. So in a way, this is kind of a good thing in the sense that I have enough of the CPU implemented that it's running for a very long time, I think, but it's so slow that like this is new, normally I wouldn't run for this long. So it's definitely going a lot further than before, but I don't think it's doing a lot of work. Okay, let me try something. What I'm going to do is I want to see if I can trap it in the debugger when the CPU throws that exception that it doesn't have the instruction implemented. So unhandled op. So that rather than doing this, fail. What is my fail helper doing again? All right, logic error. I guess I could just leave this how it was, but try to catch it instead. This is where I call execute instruction. So if I catch a logic error, for now, it's just crap. I'm going to assume that it's okay, caught exception. Or I'll say CPU exception, or whatever. And then if that happens, we'll say that we'll break into the debugger. Right. Okay. And I want trace. Okay, so how will that help me? And I need to be able to turn on and off trace. I have this set here, but I think I'll just do trace. I'll just add my own custom command for trace. Okay, so if it's trace, I'll just toggle it. And I'll say what just happened. So I'll say here trace disabled or enabled. Okay. So let's see what happens. If I toggle trace, I should be able to turn it on and off. And I should hit, when I hit that exception of an unknown instruction or unhandled instruction, I should break into the debugger. So trace disabled, trace enabled. Okay. So that means if I continue, I got a trace here. Turn it off, I should have none. If I break, okay, that's pretty good. Let me put back my colors because I don't think that made any difference. So this should allow me to turn off the trace, run. Without trace, it should go much faster. And there we go. But, oh, okay, so I got an unmapped address exception. I did not expect that. Didn't I fix this? D800? Oh no, that's it. That's what I was getting before. Oh, okay, so this is an assertion, right? Okay, so it's not an unhandled operation. So what I'm getting here, I need to know what the PC is right now. So 0x F6cc. So I think if I run my debugger and say I want to put a breakpoint on that address, set my symbols up, set this guy up, and we'll turn off the trace. We continue until we hit that breakpoint. Okay, so we're broken at F6cc. And so this is where it will die, right? No? Oh, maybe it's multiple times. Ah, yeah. That's interesting. Why would it compare multiple times? F6cc. So breakpoint hit. Then I continue. Whoops. Why is it that when I continue, it's as if the trace gets turned off? Oh, is that what happens? Let me just check something. No, it's the only place I touch trace, so no. I think what's happening here is it's not continuing. Could that be? If I step, it steps the instruction, and then it'll continue. That's super weird. That doesn't make any sense. Okay, let me just debug my debugger. So, okay, put a breakpoint here. I hit continue. So I'm not broken into debugger because I said to continue. Trace is enabled. So it prints the operation. And then I check my breakpoints. Because I want to break before. I guess I haven't tested this case in a little while, which is really strange. I want to break before I execute an instruction so that I can, look at the registers and all that. But if I'm already on that instruction and I say continue, I don't want to break on it again. How can I know? I can't know. What's the right thing to do? Or maybe when I continue, I should execute the instruction and then continue. So continue is kind of like step and continue. I think that's probably what I want. Is it? I don't know. I guess so. I don't know. Yeah, I don't know what the right way to handle it is. So I have a breakpoint at a specific address. When my program counter reaches that address, before I execute the instruction there, I break. Now, if I hit continue, okay, sorry, that's it. When I hit my breakpoint, what happens is that it says, oh, okay, we just hit a breakpoint, so let's break into the debugger. Break into the debugger. Say that we hit it. We set break into debugger true, and then that causes us to actually break out of this while loop here. And then that puts us back into the, okay, I'm broken into the debugger, at which point I print the instruction, which is actually something I don't know if I want, but anyway. And then we wait for input. And then if I say continue, I go back to, okay, so I go into continue, it says, oh, okay, you want to continue, so we just set break into debugger false, reset the last time, which causes us to then, on the next iteration of the debug loop, to go into this I'm not broken into debugger, and then once again we print the operation, and then we check our breakpoints and realize, hey, we need to break on this instructions because we haven't executed it, which means that I cannot continue past my breakpoint. So yeah, I guess continue really means step and continue, which sucks because I can't do that nicely or cleanly. Can I? Thinking of different ways to fix this. Because one way I could fix it, but it's rather hacky, is to add the notion to my breakpoints that like some kind of counter or something, and only break once it reaches 0 or something. Nah, that's like skip next or something, but it's super hacky. And the other way would be, if I want to step and run, step and continue, I'd have to be able to invoke this. Maybe I should just call execute instruction. The way I do exactly here, like when I step, right? So here I step, by printing the operation and then executing it. In the case of a continue operation, do I need to do the printing and the execution? Maybe. Okay, let's try. First step, current instruction. Otherwise, if we have a breakpoint on it, we will end up breaking immediately on it again. We won't actually continue. Okay, let's try this. And I didn't write down the the address I wanted to break on. So let's just see how far we get. Okay. So program counter, well, yeah, that's right. 0x f6cc, f6cc. So here, I'll just add it break here. Okay, so that's rather close to where I used to break. Interesting. Turn off the trace. Okay, so breakpoint hit at f6cc. Looks like my execute did not work. Why not? Execute instruction. F6cc. Just to compare. Now I'm at F6CE. Break into debugger false. Oh, yeah, no, this is working. It's because I have trace off. Okay, there we go. I wonder if I can find what this code is in the BIOS routine. Where did I put it? Here. Okay, so comp A. Not what I searched for. Okay, so I need to search for a regular expression. Print ships, really? But that's not the one. So followed by BLS. Maybe it's, yeah, it's this one. So it's like some sound routine. Continue currently playing sound here. Init music. These routines are responsible for filling the music work buffer while a sound is being made. It should be called once during each refresh cycle. If you want to start a new sound, then you must set C856 to 1 and point the U register to the sound block. If no sound is in progress, then it returns immediately, unless you call init music or init music DFT, which do not make this check. When a sound is in progress, these routines process a single note at a time and calculate the amplitude and coarse fine tuning values for the 3 sound channels. Mask out low 3 bits. Get twang value from table. Update current twang value. Increment twang limit. Go back until all 3 channels are done. BLS. Otherwise, we'd reach F6DE. Let me look at my breakpoints. So, info break, disable 0. Okay, and then eventually I hit that unmapped address error. So if I'm patient enough, right, and that's actually what I was trying to do, which was get to F6CC. It gets there, and then eventually wait, F6CC is a compare instruction. It's not okay, sorry, it's because it's been moved already to the next instruction. So it's actually this one here, it's F6CA. At one point, it wants to increment U. Okay. And here, effective address is C8D8. But I've gotten to the point where it's D800. Let me see here. F6CA is this. So what does that correspond to? F6CA here. Increment twang counter. Such a weird instruction. So saying increment the value stored at in U. Okay, I'm gonna stop here and resume next time. So thanks for hanging out, and I'll see you next time.